Okay, so the other type of problem you can have with these parallel flow situations, right, is a situation of given a head loss, right, of given this head loss, pipe dimensions, roughnesses, right, fluid properties, given all these things, is this find the Q total. Sometimes it's a situation because you can only provide a certain amount of energy with a pump in a parallel system, and you just want to know, well, how fast is the flow going to be going there? This is the easier problem, actually, when it comes to parallel, which is opposite to when it was series. This was a bit easier, right? This was the hard one in series. So, right, essentially because you know, right, you know this number, which means that you then know that this has to equal that. This has to equal that. Remember, right, for all parallel flows, this is true up to n, right, if they truly are parallel. Right, all of the head losses are the same throughout this one, and then this one. So this is just then n subproblems that you already know how to do, which are the series problems, right? So then I think in the notes I had this little algorithm you have where it's just the same Jerry process of then, okay, that would mean that this problem itself boils down to given, right, given delta H1, which you know, find the flow, right, find Q1. And you know how to do that from the previous ones where you set up that equation and you just have some algorithm solve for what that Q has to be. So then you would just need to do this n times. So like, right, for something like this, you need to go like 4 I equals 1 to, let's say, n. Right, 1 to n. You're going to solve for Qi given the head loss, the properties, and the dimensions. Right? So you do this over and over again. You find all of the Qi's, and then the last step would be, well, total flow rate is just then sum them all up. It's not too bad as long as you understand how to do those series calculations, which the whole first part of this lecture is about doing, which is just writing down that one equation, seeing what unknowns you have, and then giving it to the computer to spit out what one you want. So the parallel ones mimic that where, right, for this type of problem of find the total flow rate breaks down to n subproblems, which are just series of pipes problems, because these could actually be pipes in series. That's fine. But you would still have the means to actually go about and get that answer. There's one more multi-pipe problem, which is somewhat fundamental and is used heavily for something called Hardy-Cross method. But that's this junction concept. So abstractly, right, here's some point. I don't need to draw another picture. I mean, there's like some reservoir problem this can come up in. But as long as you're just connecting dots where each of these lines is a pipe and this is a junction, so some place where these things connect, right? The way you solve this is you just know at this, like, let's say point, I call it a junction point. You just need to state that, well, all the flow rates, if you don't even have the arrows really, without assigning arrows or directions to flow rate, which is almost like you're already making an assumption of how the flow is going, so it's better to not to do that. For each junction point in some web of nodes, right, you would need to go sum up all the flow rates at this junction point, and they have to equal 0. because you cannot generate, right? The idea is whatever comes in has to leave, so you can't generate fluid mass in a point. That's what you're saying when you say this. So, right, then if you could have complex webs of piping systems, say something that went like this, and could keep on going. So this is J, we'll call this point, we'll call that K, we'll call this point, let's say junction point M. You would write then 3 equations for each of these node points. So this would be at the junction point A. You would have another equation, sum up all the flow rates here at that junction point K, and then another equation here right? So that's now, you can write 3, right? For any junction point that you have, you can write this equation out, which is summing up flow rate, which is just summing up flow rates. And this is a statement about velocities. The other equations available for you, let's take away this more complicated one. The other equations you have available for you to write down to solve these types of things is the same head loss equations we wrote before, right? So if this is 1 to 2, 1 to 3, and 1 to 4, those are states of the system. So if this is the end point of this piping system, it could have like a given velocity, a given height, and a given like requirement. Same with all of these. So then you can also write the head equation down for each connection between 1 to 2, 1 to 3, and 1 to 4. So in the notes I have that, but I just want you to say you would write down, I'll do one of them. So, right, given going from this state to this state, you would have G this is at 1. Is that 2? Throw a room. Okay, I'll just redo this idea. The picture we're solving is this. This is 1, this is 2, this is 3, and this is 4 when it comes to piping systems. So this is, right, the energy at point 1, and I'm going from 1 to 2. So I write out the state at 1, the state at 2, and then what do you have? You have then the sum of all. And that is major and minor. I think anything can be that. So, right, that would go from 1 to 2. So this equation is 1 to 2. I could write the same one down going from 1 to 3. That would be stuff. And then I would have the same equation of going from 1 to 4. That would be from here to here. And then the one equation you have left is just, right, and I'll write flow rate in terms of this now, right? This has to be, right? All the flow rates at this point have to equal 0. So this is just my 4th equation. And just appreciate now the same trick I'm trying to get into your guys' head, that of the things that you don't know the velocities in these pipes, right? There's a velocity here, there's a velocity here, there's really a velocity coming out here, and then another velocity right here. You don't know the velocities in this piping system given pressures at the edges. That's what you're finding with these. So if I don't know V1, I don't know V2, I don't know V3, I need to write down 4 equations, and these are exactly what they are. So after you write those down, you plug it into a computer, and now you get your velocities. But you won't get anywhere if you don't just sit and realize, I don't know my velocities, so I need to write down 4 equations. What ones do I have that are available to write down? I have this fancy junction equation, and then I still have my head loss equation I can write down 3 different times. 3 plus 1 is 4. So this is 4 unknowns. With 4 for equations. And this is more important, right? This is more important than understanding how to set these equations up than I think it is actually solving these things, because today you just plug them into computers. But I've seen people spin gears, right, trying to get velocities by writing down 2 equations, just this one and maybe one of them. So that's pretty critical when it comes to multi-pipe systems, is at least understanding the unknowns that you don't have. That's why you have these engineering students with a formatted way of tell me your unknowns and tell me your givens. That's cluing you into how many equations you at least will have to write down to solve the system. So it's important for multi-pipe flows, because all your unknowns, you always can write down the head loss equation or the energy equation, and then these fancy connection equations, like you can't generate Nash in the node. That's what's saying, right? You can't just generate it. No fluid's getting stuck inside this node. So that's the zero law.